Okay. Welcome to the last hands-on session, in the last session or last talk for today, this workshop. The plan now is to first run a simulation with the Epilepsy model you just learned about, then have a quick look about how to import or how to visualize a simulation or data from mouse or from the LM connectome, because TVB also provides data or default data with this. And then we will have a quick look at the script interface. So Julie, in her talk right now, the last thing what you saw was the Jupyter notebook, where you can write these Python commands using this TVB library, and this will then also run your simulations. Okay, so we go to the simulator page to start a simulation with the Epilepsy model. And as you've heard, there was this one specific parameter, XO, which is the epileptogenicity index. And what we want to create now is a patient with temporal lobe epilepsy. So we will set the epileptogenic zone into his right hippocampus or amygdala, somewhere there, and then a propagation zone around this, and then we'll start the simulation and see if we can trigger a seizure there and how this will spread. But therefore, we will have to save 3 different configurations of the Epilepsy model. And how do we do this? Paula, in her talk, already showed us. We have to click this menu up here. Okay, let me see. Click this menu and choose the faceplane viewer. And so this, you should by now be familiar with this picture, this faceplane view. And on the left side from this drop-down menu, you can select the Epilepsy model, because this is the one we're going to use now. Okay, click on it. And so the faceplane has changed. You can play around with this, since you already know how it does. So clicking up here, you will end up in this limit cycle, as Julie showed us. And down here, we end up in this fixed point. So there's this bistable configuration. Now, on the left side, you have these different sliders for different parameters of your local model. And as I said, very important for us is this XO. This is the epileptogenicity index. And if this is above a certain threshold, the area of this brain area equipped with this model will generate epileptic seizures autonomously on its own. And if it's below a certain threshold, it will stay stable, but can be triggered from the outside to generate epileptic potentials as well. So this threshold is somewhere around minus 2.05. So above this, minus 1.6 is actually epileptogenic. And we will save this configuration and give it the name EP zone. EP zone for epileptogenic zone. And then click this button on the right, Save New Parameter Configuration. And now we will define a propagation zone so we will call it P zone, or whatever you want to call it, but you have to identify it in the end. So I call it propagation zone P zone. And we will reduce the epileptogenicity index, XO, to minus 1.8. And then hit the Save button again on the right side. Save new parameter configuration. And finally, we will also use a configuration for the rest of the brain, which is not part of the epileptogenic zone and not part of the propagation zone. And we'll just call this healthy zone, because this will be the epilepto in the healthy range, or in the range which not trigger seizures on its own. So put it below this threshold. We just put it at minus 2.2, and then hit the Save button again. So has everyone save these three configuration of the epilepto model? Yes?
Why don't we see this X0 adjustment in the graph? Like we still see the limit cycle there.
You mean why this faceplane doesn't change?
Yeah.
So this is actually just two dimensions of this 5-dimensional model, and you would see the change in a higher dimension. Yeah. Okay, so if you've saved all of them, then go back to the simulator page by clicking the simulator button. And now we want to, Paula also showed us already how to equip different configurations of your local model to different brain areas. Therefore, click on Setup Region Model up here. And if you click Setup Region Model, this window will open up. And here you have the ability to choose from this drop-down menu. So here, in my case, you can see a lot of different configurations I saved already, but you can also see the ones we just created right now. So EP zone, propagation zone, and healthy zone. Choose the epileptogenic zone, EP zone, and then deselect all regions by pressing on this empty box. And we said we wanted to simulate a patient with temporal lobe epilepsy, or the epileptogenic zone within the temporal lobe. So let's select the left amygdala, the left hippocampus, and parahippocampal region. These three. And then click Apply to selected nodes. So these three areas, or nodes, will be equipped with the epileptogenic zone. So later we will assume the seizure to start in these regions and then from there spread on into the rest of the network. Okay, now let's define the propagation zone. From the drop-down menu, select P-zone. And let's put the left temporal cortex inferior and ventral, these two regions, and press Apply to selected nodes. And now we want to select all of the other regions. I'll just do and equip them with the healthy zone. I'll just do this by pressing this button here and then deselecting the ones we already equipped. Does it work? Okay. So we now select from the drop-down menu our last configuration, H zone, and click Apply to selected nodes. So now what we see is, most of the brain, especially all the right hemisphere, is this healthy zone, and in the left hemisphere we have those different propagation zone, epileptogenic zone, and healthy zone. So did everyone arrive at this stage? If not, raise your hand or ask questions. Okay, I think we can continue. Then press Submit Region Parameters on the right, and you will get back to the simulator page. And what you will notice now is within your local dynamic model folder or field, you have the epileptor, and within the XO field, you have this array with many different values. And if you scroll along here, you will also find somewhere, so at a specific place of your region, you will somewhere find also minus 1.6, minus 1.6, and so on. So wherever the region, the left amygdala and hippocampus was stored in the connectome is now here in this array. So you could have done the same thing by just entering the array here, but it's more user-friendly, I think, if you use the setup region model. Okay, did everyone find this? Then some more parameters we want to change from the default settings here. One is KF. Instead of 0.0, we'd use 0.1. This is actually big enough.
Should we start a new simulation or something? Should we copy the thing again?
Oh, right. Yeah, I'm using a new simulation. So you see up here, there's a new simulation. Because otherwise, you cannot run. You cannot. So you can change parameters from your old simulations, but you cannot click the run button. You want to start a new simulation. So if you haven't done so, click this this star button up here in the left to create the new simulation, and there enter the parameters. Yeah, then you would have to go up to set up a region model again. To those, set up a region model. Yeah.
But it's alright. You mean
You would have to select them again. Yeah.
is there a way to load it again from previous? I already saved it somewhere.
I don't know if you've saved it.
I click this submit.
Yeah, but then this just submits it to the field. And then you. No, sorry. So the regions were the left amygdala, or let me show you again. So we have 3 times epileptogenic zone, amygdala, hippocampus, and parahippocampal region, and 2 times propagation zone, LTCV and LTCS. No, yeah, LTCI. What? LTCI and LTCV. Should I go back to set up a region model? Okay. What? No, yeah, this is, so did everybody get so far? So did everyone arrive now with a new simulation and equipping your epileptor to the different regions? Then, as I said, we have to change some more of these default parameters of your local model. One is K_F. Instead of 0.0, you use 0.1 in here. And for KS, you enter minus 0.2. And for R, capital R, you take away the 3 and enter a 1. So 0.00015. Okay, so if you have entered those 3 parameters, then scroll down to variables watched by monitors, and scroll down in this window, so you can actually scroll here, and select x2 minus x1 to be recorded for your simulation. If you scroll down, no, here, in here.
Oh, sorry. This.
Yeah.
It's already selected.
Yeah, but both are selected. We just want one.
Okay. So this doesn't matter.
Yeah, this is the next step. We'll do this in a second. Okay, so as your integration scheme, please choose stochastic coin. Within integration step size of 0.05. Oh. And we will add additive noise to your integration. But for each variable in this model, a different one. So use 0.0, 0.0, 0.0, 0.0003, sorry. Yeah. Right, it's comma seg, but it's a decimal point. No, it's a, yeah, and it's comma separated. Oh, let me show you. But then it doesn't show everything. No, I have to shrink it. Okay. Can you see this here? So has everyone got this? So D is the dispersion of the noise. It's not a range. It's for each of the state variables of our model different. Oh yeah. Oh, perfect. See. Yeah, I just learned something about TVB. Thanks. So if you have not entered the array by hand now, you could have also done it here, entering the dispersion or the variable for D in the window and then apply to each node. Yeah, then you have, okay. Now, as your monitor, choose temporary subsample with a sampling period of 1, and we will calculate 10 seconds, so 10,000 milliseconds as your simulation length, please. This is one of the monitors. You don't save every step of your integration, but just each millisecond. So our integration step size is 0.05. We won't save so you could choose raw recording. This would save every integration step. And temporarily subsample is just each hundreds or 50s or so on. Okay. So we have to give the simulation a name. And then press the play button.
Question
Yes?
Existed before, so it's a common model?
Yes. You mean who developed it, or? Yeah, I think there's a question for Julie.
It was developed in the team of Marseille.
In the course of this TVB or
It was no, we implemented after in TVB to simulate on a break network level.
But we can show you the original paper of this model.
Okay, my simulation is finished. How about yours? Some are laughing, some are shaking their heads. We just wait a few more seconds. So whose simulation has finished? There are some hands. Okay. Some more hands. We'll wait a little longer. Okay, I think I will proceed on the screen, on the main screen, so you can see the results even if it hasn't finished on your own computer yet. So you click time series region again, choose the visualizer, and choose brain activity viewer in 3D, 2D. So you are familiar with this picture already. Sorry. So what we see in the beginning here, there's a lot of spiking and fast oscillation going on already. And it should actually, at some point, stabilize. So due to that we didn't set, or we cannot set in the graphical user interface, we cannot set the initial conditions. We in some regions we start within the seizure state, and then over time it settles, and we return back to the healthy state, and from there on we could really observe how a seizure spreads. But you see, this is not the case in my simulation here, and I wonder why. So, but I have prepared another one where I actually use the exact same parameters. Let me show you this one. Yep, so in the beginning we have those fast oscillations. But you will soon, we will just skip the beginning part. And we will watch the brain from the inferior view. And so now this is the moment where all the regions are still stable, right? And what you will see now is we will some fast activity or some fast discharges around this area. You will right now see color changes here. And then you will see how this fast activity will spread first through our epileptogenic zones, then the propagation zones, and finally onto the whole left hemisphere. It'll fast forward. Okay, so this is what you should also see on your screen. Did the simulation work for anyone? No, for no one? Actually, it should be the same parameters. Right. Right. Yeah, healthy channels are still the epileptor model, which can be triggered from the rest of the network, but would not create seizures on their own. But it's strange that. So what does your simulation show? Exactly. Like this exactly. So we all did the same mistake then. You all followed my mistakes, yeah. I know what we missed one thing, yeah. But it's really just one parameter we didn't set. So go back to the simulator page and copy your epileptic simulation.
So this actually shows if it doesn't work, it's not TVB's fault.
Thanks. Thank you, Misha. This is actually that's very a good lesson, because Randy told this morning. One of the pitfalls of TVB is misusing coupling function. Was your last slide, I think, the pitfalls or traps of TVB, and this is what we've done here. So instead of using difference coupling, we use this default linear coupling. So we have to change this. Please use difference coupling, and put A equals 1. So the rest should stay the same as right before. So simulator page. Copy. Okay. So here you would have to change some local parameters, R, KF, and KS. Copy them from there. Then for your monitor, choose this x2 minus x1. The integration scheme is stochastic coin with an integration step size of 0.05. And then additive noise as we've seen before. Yeah. Temporary subsample and then 10 seconds. So I hope it. And then, yeah, press play button and run the simulation. Is it still running? Yes. Okay. Yes, you can. Go to project, click project, and click on operations. And there is this pause button or cancel button here. If you click on this, you can stop your simulation.
Just one practical issue.
Of course.
Some of the simulation that use the 100% of the CPU, and this one is probably something 40%. So if this, I want to install the TVB on the server that's shared by several people, then how is there a way that I can adjust the usage and the CPU usage?
I think this is a question for the software developers. But TVB and cluster usage, the main issue is how to parallelize this. And in TVB, as far as I know, those parameter space exploration we've looked at today are done each on a separate core. Right?
Sorry,
the parallelize, or he's asking about CPU usage in TVB and on how to, when it's installed on the cluster.
The way TVB parallelizes simulations at the moment is only if you have two concurrently running simulations or if there is a parameter space exploration. We don't parallelize one simulation.
The overhead is very any way I can adjust it, like real time, like I can move up or down the bar that I can use certain percentage of CPU while computing or before start the simulation.
Oh, you want to limit how much
Yeah.
CPU you are allowed TVB to
Yeah.
consume? There isn't an option for that that comes with TVB, but using your operating system, you can jail the process, the TVB process to do that. So this depends from your operating system. Your operating system, there are ways to actually say to the operating system, I only allow this process to consume this amount of quotas of resources. But that's out of the scope of TVB. By default, it will eat your machine. For the region model, I've only taken this question and then let me continue. For region level simulations, those are intrinsically not parallel. In many problems, when you can parallelize, you parallelize essentially in space. You have many things that happen at once. For region simulation, there are only 60 nodes that do something. It takes a long time because it's temporarily long, the computation. And that's coupled, temporarily coupled. I can compute something before I've computed the data that it depends on. So it's intrinsically hard to parallelize this problem. I don't think it can be. If you have huge spatial components, if you do certain simulation, or if you have hundreds of nodes, then it starts to make sense. Otherwise, the problem doesn't allow. It's not parallel. It's not a parallel problem.
Okay, so my second simulation with the correct coupling function finished. I don't know about yours, but to me this result looks no better. So as I said in the beginning, we start with some random initial conditions, some seizure, some areas show those spikes, even they're not seizure-like independent, but this is due to we cannot set in a graphical user interface. That's why we're using the script interface a lot. But after 2 seconds or so, your simulation should stabilize, and then you see those seizures approaching. And actually, you can see here in the hippocampus, the left hippocampus is the first area to show this epileptic seizure, and then it spreads to the other region and finally to the whole left hemisphere. Is that the case for your simulation as well? Yes? No? I see some people. Yes? Some people no? So please ask question if it's not the case in you.
If you run this simulation twice with the stochastic model, you don't get the same result every time.
Yeah, there's a noise input which is random, and initial conditions should be random too. So, and no with stochastic integration, no two simulations should be the same. Yes. That's seed, but it's not the. Is it the seed for noise for the integrator as well, or is it for the initial conditions?
I think it's for the initial conditions only.
Okay.
I will have to check that.
So in the script interface, yeah, of you. Okay, now here we can see how the seizure starts in the hippocampus and then spreads. And as said, so this is going to cycle. After a while, this is going to stabilize and then begin again from the same position. Yes? Color is just the intensity of the scale of the time series. Good. Are there any more questions about the simulation? Were at least some people able to reproduce this? Yeah. Okay. Good. So something we haven't talked about today, or there was no talk about, no presentation, is how to use TVB and the setting of other species. And one of them is the mouse. If you go to connectivity, you have this menu open up where it says one option is the LN connectome builder. So this is an implemented function or a pipeline which will automatically download and generate a connectome from mouse from the LN connectome tracer study database. So you can insert your features or the resolution of your connectome you want to have, and then hit the launch button, and this will automatically establish a connection and create the connectome. Because this takes some time, TVB already provides you with one LN connectome, and we will now try to upload this one into this default project, and we want to try to visualize this mouse connectome as well. Therefore, go to data structure. So click project, and then go to data structure. And on the right side, you have this upload button here. So click this, and from the left menu side, click TVB HD5 zip. Now, you would have to find the LN connectome. For Mac users, it's inside this app. So open it. Package content. And then in here, let me show you like this. So there's a path you have to follow, resources, lib. So it's hidden deep inside the structure. But we will copy this to our desktop. Python 2.7, then TVB data. And there's mouse, yep. The LN 2mm connectome. Just copy this folder and paste it to your desktop or wherever you want. It makes it easier to upload then. There's a demo script, yeah, for the mouse connect, yeah. But we're just trying to visualize this in the graphical user interface now.
There is no like TVB app for Windows users.
So you would probably have an equivalent.
Where's the Windows?
For Windows users, there is a TVB data, which is much more, yeah. And then in TVB data, you will find the same structure. This was not meant to be used like that, but we'll find it. You know what? If you have a find function,
Yeah.
you'll find Alan. It's easier like that.
It's on the TVB data library
Alan
site.
2mm should be the one. Okay, and just copy it there. So,
All of them.
just copy the wrong side.
Yeah, in this folder there are 4 files: connectivity, region volume mapping, structural MRI, and volume. And just copied. I copied the whole folder to my desktop to have it ready for the upload. So did everyone find the LN connectome? No. Mihai, can you help him?
So
What? Right, you import one after another. By this function, you import one after another, all of these files. This is now in TVB format, as I said, generated by this built-in function. Right, so they are exported already in TVB format under the name John Doe. So they will appear at the same within the same subject. Right, it's not human, it's mouse. All of them. Has everyone found the connectome? Yeah? What? You get an error message? There is already one with the same name, so you have imported this already somewhere.
Where?
If you scroll down,
It's far down.
So this error message appears when you try to import a file which is already imported. So TVB gives each connectome and each simulation a global identifier, GID.
Okay.
So there are no doubles within there.
Where do I mean, this is all the data, right?
Right. So it is stored as well in John Doe, apparently, raw data. Yeah. And there should be something like volume. Do you import the volume?
I didn't import volume that I imported. I went from
The connectivity.
right.
So but then you probably have it already in there. The latest one from today evening, yeah.
This one.
If you use Visualizer. Ja, das ist der Mauskonnektor.
Das mit der Sortierung, wenn man es nacheinander importieren muss, ne? Da hast
Genau.
du jetzt-
Ja, es gibt nochmal einen Fehler, wenn du diese Sache importieren musst. Weil die Connectivity-File so nicht abgefüllt ist, hat schon.
Hast du das schon erklärt?
So did everyone find the connectome? Then we use this upload function, TVB-HE5, choose the file you have and start with the connectivity. Yeah, and choose upload. So this is interesting. I get this error message. There is already one connectivity with the same name or GID, global identifier. So in preparation for this workshop, I uploaded the Allen connectome already, and TVB gives every connectome an identifier, so you cannot import something twice. Yeah, there's no mismatch in the end. So this is why I get this error message. But you shouldn't get it if this is your first time. You import this, and this raw data should also appear below John Doe. So don't get confused. This is not human data. It's still mouse data.
Visualize it.
What did you visualize?
I click one of those raw data.
Yeah,
So,
yeah. This
first column
is
there.
human data. This human data. This will look like human. Yeah,
But I did upload it.
yeah. All four of them.
Try like there's some error messages.
Yeah, you don't have the region volume mapping yet.
Should I create a new project and
Maybe, yeah. Create,
how do
you
I-
can list of all projects
Just like, oh, okay.
and then create a new project.
New project. So I go there. Then save, right?
Mm-hmm.
For
data structure and then try to import it again. So if you have imported all 4 files, you will find somewhere in your John Doe raw data this file called region volume mapping. And if you press on this and choose the visualizer, you will see this region volume mapping visualizer, and if you open this up, you will actually get the region volume mapping of your MOS data set. So what you see in the background is this structural MRI scan, and overlaid on it is this region mapping where each voxel gets assigned to a different region. And you can then scroll through this and look at different angles. There should be region volume mapping. Have you imported all 4 files? Yeah. Which? Like they are listed, I think. Because they also depend on each other. You cannot import like a volume if there's no connectivity, which it is relying to. I think your TVB died.
Oh.
If it's completely red without
another
an.
one time. It just dies every 10 minutes.
Yeah. You have to restart the application, I think. Completely restart the program. Yeah, like they're there.
Like they're where?
Connectivity, yeah.
I imported this, but then the other.
Then volume, yeah. Does it work?
Well, I've imported the connectivity.
Yeah. And then TVB HD5 zip, yeah.
Okay. So
and
now
then
I have to choose the other ones.
Choose volume now. Choose volume. Yeah.
Okay.
And then upload.
And then I go for the other.
Mm-hmm.
So that means upload.
Sorry again.
Yeah.
I tried this. That's the only one loaded. All the others reloaded.
Yeah, because it's you have this already in the other.
Sorry, what's supposed to be the order? Correct order.
But you have this already in TVB in the other program, sorry, the other project, and it still reads it there.
So it's okay. What's the problem now?
Ja.
Und dann, was machen wir jetzt hier?
Klick drauf.
Aber das ist richtig.
Nee, da ist Region Volume Mapping.
Wo ist das?
Da muss noch ein Region Volume Mapping sein. Bei der das ist noch nicht drin, glaube ich.
Ach so, also wir haben nur Connectivity und Region Mapping bisher hochgeladen. Das ist falsch.
Volume?
Ach, Volume. Okay.
Und jetzt Region Volume Mapping. Das ist noch nicht da. Du musst auch noch, oder? Wort aufeinander auf. Okay, so I hope at least some of you have managed to upload this Allen connectome, and since we are already over time, I would like to continue at this point. So all of these steps we were trying to do in the hands-on session are also recorded on your stick. There's a hands-out. All the slides of the other talks are on there, and then also there is a hands-out with pictures, screenshots, where to click on to do the different stuff for the epilepsy simulation, for the stroke, for the parameter space exploration. And also one thing I want to mention is that if you have any questions about how to use TVB, blocks, arrows, how to use it for your specific research field or question, you can always ask us on the TVB mailing list. I think virtual brain. So on here you can find, actually where is it? Here's the Brain Simulator, yeah. Yeah. And here's the docs, and here's also our mailing list. So this is very important. There are people already ask a lot of questions about TVB there, and we try to answer them as soon as possible. And not only we here in Berlin, but also our colleagues from Marseille and Canada. And now to finish this up, I just want to show real quick the short example of the script interface. So did we show you already how to open it? There should, yeah? Okay. So if you open this, there you will find all these demo scripts, which are very nice. I can really recommend to open those and go through them, because a lot of them have a lot of comments in there, a lot of documentation, and explain what each command in the script interface does. And what I'm showing you here is with just, let me count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 lines of code, we can run our own simulation. So what I wrote down here is I imported, all this is Python code executed in this Jupyter notebook. So you write your Python code within these cells, and then execute them pressing on play button here, or shift and enter. And here we load in the TVB library. We create a simulator object, and we actually really define all the same settings we were defining in the graphical user interface. So here this was what I was talking about. Here we can set random initial conditions, or we can set initial conditions on our own. Here I used random, so that's okay. We define a coupling function. Here I chose linear coupling. We choose an integrator, deterministic here. We upload a structural connectivity. You can even say load default, which will really use the same one we were using the whole day in the graphical user interface. We specify a conduction speed. SL is, in my case, just the simulation length. We use a local model, in this case generic 2D, which we already know from today. Define a monitor. Push this all together in one simulator object. So this is what you can see. We define all this stuff here. And then we can get out, we let us give out this simulator object. You see random initial conditions defined, linear coupling function, our integration scheme, and so on. And then there's really just one command. Once you defined your simulator object, you press sim.run and then brackets, and this will print the outcome of the simulation into your variable. And here I'm plotting this. And just to show you that it works, let's change one of these parameters. So A was this coupling scaling factor, and then I run all these cells again. Okay, see, this was the impact. This is the same story as we were using in the first hands-on session, generic 2D oscillator which ends in this fixed point, and I just reduced coupling, so regions end in a fixed point, and if I go back up here and increase coupling, we're there with sustained oscillations in our network. Okay, I'm sorry this was a very short or brief excursus through the script interface, but since we're a little bit short in time, I hope this was okay. If there are any more questions, please ask them.
Okay, thank you,
If
Paul.
not-
Okay, and it's time to end the workshop. I hope that you enjoyed the workshops, that you learned a lot. So there will be much more to learn in the future. And as Paul already mentioned, you can get in touch with us. You can use the mailing list, and there will be always help available. So for now, I would like to thank you for participation, for your active participation. I would like to thank the speakers and all the TVB staff for their help. And particularly, I would like to thank Paul Triebkorn, who organized the entire event. Thank you very much. Well done.